Good afternoon. We are just running a little late, but hopefully we'll catch up. And it's my great pleasure to introduce Professor Bob Ergun. He has the benefit of being at the University of Colorado Boulder at LASP. And Bob is known for having played a leading role in multiple missions to do with kinetic physics, something that we have discussed in previous lectures. Talked about kinetic theory, and Professor Ben Chandran from UNH told you interesting things about kinetic effects in the solar wind. Well, Bob has played a leading role in the MMS mission, which is producing all kinds of beautiful path-breaking data for both substorms and reconnection, which is the theme of his talk.
Okay, well, thank you. Thank you. Can you hear me? Is this working now? Good. So I'm a local, and so that's why I haven't been hanging out here a whole lot. It's always an advantage and a disadvantage. So I want to first welcome you to Boulder. I know that Dana's been showing pictures of buffalo and bison throwing kids around or something like that. I can't remember. So I thought I'd show you what I saw out my front window just 2 weeks ago. And I thought, oh, well, this is really cute. Can you see that? Is there a pointer here? Here it is. You know, there's a baby bear there. Can you see the little baby right there? Oh, it's so cute. Mama and baby, I thought, you know. Well, I went to my back porch. And there's baby bear. There's mama bear. So, I don't know. We have some interesting things here going on in Boulder, too. All right. So let's talk about not bears, but magnetospheres. There is so much material here that there is no way that I was going to cover this topic. You're going to see me again tomorrow morning in just 2 lectures. There's just so I nonetheless just put in 90 slides and decided I'd just give it a try, and so we'll see how far we can go. I'm, as Professor Bhattacharya has said, I started out as a kinetic plasma person. Actually, I was a theorist when I started. And I ended up building instruments, seeing the light. Sorry. And I want to, but I'm going to do the opposite. I'm going to talk about MHD processes. And I'm going to first start out showing that you could actually design a magnetosphere very, very easily with just one simple equation, which is just pressure balance or force balance. And that you could go a long way with that. You can get most of the picture out of that. But without the kinetic physics, which is the heart of reconnection and the heart of acceleration and the heart of a lot of the processes, the wave modes, you actually will miss a huge amount of the physics that's going on. So as you listen to this, there's so much rich, deep plasma physics that goes on in a magnetosphere. That is what I mean by I'm not going to be able to cover it. So you all know that there are, you know, in basic plasma physics there's kinetic, and then you could go to 2-fluid. How many of you know this? And then go to MHD. Just want to get, you've all seen this, right? This is like a Vlasov equation. Most of you know this. And that if you reduce that, you could get you get an equation for electrons and an equation for ions, and we call that the 2-fluid, and you could solve a lot of things. That's what's in Chen. Most of you have had that book, I assume. And then if you combine these, you can go to MHD, which is a single fluid. And you know, in our school, MHD is done in the astrophysics department because MHD is an approximation. It is. It's an approximation. You have to have greater than the ion gyro radius. You can't have really high frequency waves or anything like that. So the physicists don't like it because it could be wrong, but the astrophysicists like it because it's useful. Okay? Whereas in our university, kinetic physics is all done in the physics department. They barely talk to each other. Heck, even their computers won't talk to each other. But that's the interesting thing about kinetic physics is that it's much, much more accurate, but it really isn't that useful because you can only operate in a very small domain. And so the astrophysicists call the physicists useless, and the physicists call the astrophysicists wrong. Because as a physicist, you could be useless. That's okay. It's a cardinal sin to be wrong, and it's the other way around for astrophysicists. So I'm in the astrophysics department, by the way, but I graduated as a physicist, so I'm both wrong and useless. But so that's where I'm coming from on all of this. So I'm going to start and go backwards. I'm going to talk a little bit about how you actually do physics. Is really you start with MHD because that gives you the big picture. That gives you the surroundings. That gives you the whole background. And then you have to go to kinetics whenever things get a little too out of bounds or you start violating the MHD principles. So that's what we're going to go from is MHD down to kinetics. So you can see I'm going to start with describing the structure of a magnetosphere with just really simple equations, and then we'll try to identify, probably tomorrow morning, what kind of processes, and I'll try to give a smorgasbord of all the processes. So let's get started. I have now 89 slides left and not quite 89 minutes. So you've seen this picture of a magnetosphere. And let me, where did I lost it. The basic idea here is that you have the solar wind, and what is a magnetosphere? You could make up every definition you want. It's pretty much a region of influence of the magnetic field of an object like a planet or a moon or anything. And so the solar wind contains primarily ram pressure, and we'll talk about that. And that meets this obstacle because plasmas are frozen into magnetic fields, and they can't cross magnetic field lines in ideal MHD. So they have to find their way around this magnetosphere. And what first sets up is a shock, and it's called the bow shock. And that's because the solar wind is supersonic and super alphanic, meaning it's Mach 10-ish, Mach 5, something like that. So when it, just like the nose of an airplane, you're going to get a shock because you can't send waves upstream. The solar wind does not know until it hits that shock that there's a planet anywhere around there. There's no information except for maybe a couple wandering ions going upstream. That it has no clue that it's going to hit that planet. The shock simply acts. It's a permeable boundary. It's not a boundary where anything goes around. It's just simply a edge where the plasma is going to slow down. It's going to compact in density, and it's going to heat up quite a bit. And now the sound speed, it's no longer traveling supersonic, so it can divert its flow around this object at that point. All right, so we're going to talk about this with just one equation. And how many of you have seen this equation? All of you? Good. I don't have to go through this very long. There's a acceleration. This is Newton's law, right? This is force, and that's ma. It's just written backwards, but it works. And you have particle pressure. You have acceleration, and this is convective acceleration. A lot of people get this wrong. If you were to actually follow a particle in a fluid, that would be actually dv udt or dv dt. I use u, by the way, to represent fluid velocity and v to represent particle velocity, so there's no confusion. This basically is because we can't tell one fluid element from another, and if you look at it, it's basically slowing down always in the same region of space. We'll talk about this. This is the particle pressure, this is the magnetic pressure, and this is the tension. Magnetic fields don't like to be bent, so when their desire is always to straighten out. And if we want to make a time stationary model, you just get rid of time derivative. That's always nice. But you can't get rid of this convective derivative. Very important, because with this, if you rewrite this, because the continuity equation tells you the divergence of rho u is 0, you could just move this inside there if you're 1D and compressible. A lot of theorists are going to yell at me because there are a lot of situations where this doesn't work. In fact, if you take Bernoulli's law, which is incompressible, you get a factor of 1/2. So be careful with that one. And we call this ram pressure. Basically, this is the pressure that a fluid flowing right at an object and hits it. So if I took a fire hose or a fan, let's just say, and aimed it at you, that's the force you would feel, is that field, the rho u squared force. So we're just going to, for the time being, we're going to keep these three terms and throw, we'll add in, we'll talk about this later, because we don't really want to make this complicated. So if you take this and you write this as grad rho u squared, you can get this very simple formula, which I assume many of you have seen, that the ram pressure plus the particle pressure plus the magnetic field pressure must be a constant. So let's do this. This is an easy way to start designing a magnetosphere. Just with that one simple equation that the magnetic pressure plus the ram pressure plus the particle pressure has to be constant across most boundaries. So we're going to start with the front here, and I'll move back. You have a bow shock. We've talked about that. This region in between the shock and the magnetopause is that's where the that is an nearly impermeable boundary. We'll talk about that later, about how impermeable it is. But it's a boundary where the flow is diverted, but on one side is dominated by the magnetosphere or the magnetic field of the planet, and on the other side is shock solar wind. And that boundary is somewhat impermeable, so the flow has to go around it. This region in between is called the magnetosheath. So we're going to look at solar wind, magnetosheath, and magnetosphere on three different regions of these boundaries and look how magnetic pressure works and how this formula works. If you go out to the solar wind and just take some typical numbers, most of you have been they must have been telling you about solar wind to no end by this point. One sees that it's around 400 kilometers per second, has a density of 5 to 10 per centimeter, temperatures around 10 eV, and magnetic field could be 5 nanotesla or something like that. Those are just standard values of the solar wind at Earth. At Jupiter, they're going to be somewhat lower when Fran gets to talk here. But they're not going to be that much different, to be honest with you. And if you calculate these three parameters, this is the ram pressure. By the way, a Pascal is just an unit of, it's MKS unit. That's all it is, of pressure. Okay, so it's actually the same unit as energy. So this is 1,000 through 1.3 nanopascal, or 1340 picopascal. But you'll find its pressure, well, that's just NT. Multiply these two numbers and put Boltzmann's constant is 10 picopascal. And b squared over 2 mu naught is 10. So the total is 1360. But you really need these two? No, it's all ram pressure. The solar wind is just plain ram pressure. So to a magnetosphere, it really doesn't care very much about, to first order, to lowest order about what's going on in the solar wind. It just wants to know how much pressure it has. But we'll find out that the clock angle of the magnetic field is very, very important as well. I'm going to talk a little bit more about shocks. Again, there's so much fascinating physics that can go on. I could give you a whole lecture on shocks. They're that fascinating, about how the ions reflect and how they heat up and how what happens in a shock. How many of you know about Reinke-Hugenow jump conditions? Some of you don't. Okay, so I'm not going to go into that. All you have to know for shock basics is the density goes up, meaning that it's a compressible fluid. When it hits the shock front, it gets squeezed. The density goes way up. Right in this thin layer, the density jumps. The velocity goes down because the amount of particle flow is V times n. That's the amount of flux or fluid you have flowing. That has to be a constant. So if the density goes up by a factor of 4, the velocity has to go down by a factor of 4. Okay? And 4 is a magic number because that is the most compression you can get out of a adiabatic shock. Also, the magnetic field gets compressed. So we're just changing. All this stuff goes through this boundary. It's really no magic, but the magnetic field is going to get higher. The density is going to get higher. The temperature is going to go way up, it turns out, because a lot of things get heated on the shock when it gets compressed. Not just by a factor of 4, but by a lot more. And the only thing that goes down is the particle velocity, so it goes much slower. So on the other side of the shock, typically in a solar wind, and the compression factor of a shock is how much you slow it down or how much you compress the density. And you'll learn if you ever take shocks that a factor of 4 is about all you'll get for a high Mach shock. It gets lower, of course, if you have lower speeds. You can now see that we're traveling at 1/4 the speed, 100 kilometers per second going in here. Density's now gone up to 20. The temperature's gone all the way up to 250 eV, and these are very typical numbers. I mean, they vary quite a bit, but you'll find that has to be a pressure balance across here. And if you look at it, the ram pressure now has dropped dramatically to about 340 nanopascal, picopascal. The particle pressure is kind of dominant here. Not like the solar wind where the ram pressure was it. You can't just ignore the other pressures, but it is the big dominant pressure here. So now we've taken ram pressure, and what a shock does is take ram pressure and turns it into particle pressure. Okay, nature's really smart, isn't it? I mean, it just figures out how to do these things. Okay, sound speed, now this flow is lower than the sound speed because the flow has gone down and the sound speed has gone way up. And so now it's subsonic flow. It can now move around. It now can feel this obstacle and start flowing around the obstacle. And the magnetic field's gone up somewhat. So in the magnetosheath, in this region here, you can't, really it's dominated by particle pressure, but you really can't ignore ram and other pressures either. That would give you a little bit of an error. All right. By the way, any questions? I mean, anybody wants, interrupt. Ask questions. I don't bite. So now let's go into the magnetosphere. Now this is an impermeable boundary, so mostly, as I like to say. So this is just what the Earth is presenting on this side. There's not much interchange of plasma flow. We'll find out later there is, but there isn't a whole lot. So it's got its own, makes up its own mind. It's got very little velocity. It's got a very low density, but extremely high temperature, kilovolt. And the magnetic field's jumped by quite a bit now. So what do you have? You have 1200 now. What's our dominant one? It's basically the magnetic field pressure. So all of a sudden, we've gone from ram to particle to magnetic field pressure. These are the three basics that happen throughout a magnetosphere. You simply are always exchanging mostly between particle pressure and magnetic pressure, but when you add the solar wind, you get ram pressure. So you could see just by pressure balance, I could start drawing these pictures pretty easily. The in-between region is, well, it's got all three of them in there, but mainly dominated by particle pressure. So this is the basis of the front side of a magnetosphere. The front side is dominated by the fact that there's a supersonic solar wind in the case of the Earth and in the case of most planetary objects in our solar system, because our solar wind is supersonic. Most are. from other stars, we could see that. So just this simple equation, this simple continuity equation can go a long way. We could go further than that, and Fran's going to like this because she's going to talk about Jupiter. And we could calculate a standoff distance. And the way we do that is we realize that the solar wind is dominated by ram pressure, and these three are equal, and the magnetic field is dominated, the magnetosphere is dominated by magnetic pressure, right? So these two must be equal. The ram pressure out here must equal the magnetic field pressure inside. And so if we just equate those two, just say that the ram pressure in the solar wind is basically equal to the magnetic field pressure with a fudge factor. Fudge factor, by the way, is about a factor of 4 or 2, depending on whether you want to square B or not. The reason is that B is actually increased because it's compressed. So we have to be a little trickier when we do the real calculation rather than my sort of hand-waving way. So you end up with balancing this ram pressure and the magnetic field pressure with our little fudge factor. It's called the compression factor. And you also take the idea that B is 1 over r cubed. Right? So as the further you go out from a planet, this will work at Jupiter. This formula almost works at Jupiter. And what happens then, if you equate these and do some manipulation, you'll find that the standoff distance is the 6th root of the solar wind, of the inverse of the solar wind ram pressure, but also, proportional to the cube of the magnetic field at the planet's equator. And that's just its base magnetic field, one Earth, one planet radii, what the magnetic field is. So this actually is interesting because this could tell you exactly where you expect the magnetopause or the shock to be, depending on how much solar wind pressure there is, right? If the solar wind pressure goes way up, it's going to compress you. You're like a sponge. You're a mattress, the magnetosphere. If it's very low, the magnetosphere just expands out into it. But that's the 6th root. It really doesn't change a whole lot. It's amazing. At Earth, for example, it rarely comes inside of, say, 9 RE, 9 Earth radius. It's typically around 11 or 12, and it rarely goes outside of 15 or 16. So there's a range where we know where it's going to be. This is good for a person like me who builds instruments because we know where to send our spacecraft if we want to study this region. At Jupiter, you'll find, or Saturn, you'll find this thing's way out. It's much further out because the ram pressure is lower and they have very, very strong magnetic fields. So it expands and becomes different places. So this is the basic idea. One formula. So my point is, the first thing you do as a scientist in almost anything you study is you take the simple, we used to call it back of the envelope. They don't have envelopes anymore. What do they call it nowadays? What? Back of the napkin. Okay, napkins, you still use napkins. Good. It's a good thing. Back of the cell phone calculation, right. I mean, that's essentially what it is. We always used to call it back of the envelope because we'd always get junk mail, and you just take the envelope, flip it over, and you do a calculation on it. You always want to do the laugh test. Is this, you come to an unknown, let's just say, exosystem, and you have the solar wind, and you have a planet with a magnetosphere. I would, with this equation, I'd flip the envelope over and find out how close that is. If this is less than the planet radius, then you know it's not standing off. If it's Mercury, for example, if you were to calculate it for Mercury, you'll find that this is less than 1 Mercury radius. Therefore, it doesn't stand the solar wind off. The solar wind just clobbers it. If you go to a planet like Jupiter, you'll find this is 100 Jovian radius or some ridiculously large number. And you got to understand that magnetosphere is huge. Okay? So these back-of-the-envelope calculations give you the idea. But there's a lot more physics to go to do something. This is just an example of how we start looking at magnetospheres. All through this magnetosphere, you're going to, I keep thinking this is going to flip, and I keep pushing the button and nothing happens. All through this magnetosphere, you're going to find that we can do these same simple calculations with pressure balance. We could put pressure balance to deal with the lobes. These are very magnetically pressure dominated. In the central region here, we have what is known as a central plasma sheet, which is dominated by particle pressure. Because the magnetic field's reversing, it's got to be zero in the center there, somewhere, or near zero. So you have magnetic pressure here, very little here, and very high magnetic field in the lobes. And in the center, it's made up by particle pressure. Again, the magnetic pressure and the particle pressure are going to balance each other. No ram pressure back there, very little ram pressure, I should say, back in the tail. So you could, the first thing you do when you study any region is you simply take pressure balance and try to work that through. All right, I skipped over shocks. And shocks are very important in the sense that they change the solar wind. So everybody says, oh, solar wind entry to the Earth. Well, the solar wind that gets to the Earth, by the time it touches our magnetosphere, is changed dramatically. It is slowed down, it's compressed, it's heated up, and the magnetic field is increased. So all those things happen due to this shock. Shocks are actually very easy in concept, but complicated. The algebra gets very, very long when you deal with shocks. I don't know if any of you dealt with shocks. You end up with many terms. You almost have to be a good accountant, not a good mathematician as much as a good accountant to balance this. I'm not going to go through that, but I want to point out there's two different types of shocks. And one is called a quasi-perpendicular shock, and that is when the magnetic field actually is perpendicular to the shock normal. It's called quasi-perp that way. That's just a definition. Some people want to call this parallel, but it's not. So the magnetic field is you cannot have particles just entering into this magnetosphere. The magnetic field has to go through the shocks basically sideways. It's quasi-perpendicular shock. And then on the other side, we have a quasi-parallel shock, which means that we don't even need the magnetic field. In this region, the magnetic field doesn't get compressed that much because it's the perpendicular component that does. But this is highly turbulent and very, very, as you can see by the wiggles, very different in an extremely large region. Shocks also tend to reflect ions. And they do send some ions back upstream, giving the solar wind a little bit of a hint that there's something coming up. But other than those reflected ions and some reflected electrons that come upstream from the shock, the solar wind as a fluid has no idea it's about to smack into the Earth. Okay, once it passes through this shock, you have what is known as magnetosheath plasma. And so when we talk about solar wind entry, yes, this is solar wind. As an experimentalist, how would you tell something with solar wind origin versus Earth origin? Anybody know? Somebody's got to know. How would you tell? I gave you a scoop of plasma so you could do anything with you want. I'm going to pick on you. Because you looked at me. Everybody else is looking away now. How would you tell if I gave you a scoop of solar wind plasma versus a scoop of Earth plasma? How would you tell? What's the solar wind plasma made out of? Abundances. Do you have any helium double plus alphas coming off of Earth? We do have helium coming out of Earth. It's singly charged. Sun, it's doubly charged. So if I saw alpha in there, I would know that's from the solar wind. You can't tell from protons. Forget it. Protons, they all look the same. Darn for things that you see one, you've seen them all. What about oxygen? Oxygen comes off Earth too. It's singly charged. Off the sun, how many charges? 6? Yeah, 6. So it's stripped of 6 electrons. You see an oxygen atom or ion stripped of 6 electrons. That's from the sun. That did not come from the Earth. That takes that takes a heck of a lot of bombardment for that. So that's how we do it. We tell by the abundances. You got it partially right. Abundances of the various ionization states of particles. And if you went out with a satellite here, you would find a lot of helium, double plus, alphas. So that's the solar wind plasma. On this side, you're going to find primarily protons and some singly charged oxygen, which leaks out of the Earth. And some singly charged helium, not a whole lot of that. That's what you're going to see on the other side. So you know that there's an Earth origin plasma on one side and a solar wind or a sun origin plasma on the other side. Okay. So this is what the shock does. It basically modifies this. That shape, if you don't believe me, sometimes it's easier to look at something really far away to see it. We can't see our own shock, but we could take a picture of a star that is in an interstellar medium and you could see here that there must be some ram flow going into this. What the image is in the infrared. So this is the glow from the heat up of the shock, because shocks superheat when they slow down. They really give it much more heating. And so this is glowing. I don't know what the heck that is, or some of these other things, but just look at the basic process here. And that's what our Earth, very much. Just use that image. So when we draw this, we could see that the magnetic pressure of the Earth falls away in all directions, so the shock sort of fades away as you move away to the sides. Okay. So shocks are, in that sense, extremely important. We can go on and on and on with that, but I'm going to stop and talk to you about this next boundary in. So we talked about the various plasmas. We have the solar wind. We have then the shock. And then we have the magnetosheath plasma. And now we have this magnetopause, which is this boundary between the magnetosphere and the magnetosheath. So this boundary is an interesting boundary in the sense that the big question 50 or 60 years ago, or even longer, I guess, how long? 60 years ago, 70 years ago, was, is that impermeable or not impermeable? Okay. How do you, is that boundary an absolute boundary or is it an open boundary? Can we let solar wind plasma in, or is it just kind of forbidden, except for maybe through some leaky points to get in? And I'm going to talk about this. If you have a magnetic field line, this is my magnetic field line. Yes, this is whatever planet you want. Earth turns square, by the way. I don't know how. But when you have a solar wind magnetic field line coming at Earth, it could be some sort of random orientation like this. It has couple choices. It could go around. You see that? It could just simply bend. I got to bend it. You could simply bend and go around, right? And that would be called a closed magnetosphere. So why wouldn't it do that? Okay. Another option is that it could hit here, but then what's going to happen? It's going to bend and bend and bend, and what's going to ultimately happen? It will break or reconnect, as you've been, no doubt, told many times. In which case, you now have opened up that magnetic field line. You have connected a part of the Earth's magnetic field to the solar wind. Maybe I should draw this on the board in my infinite artistry. So what we have here is, let's have the Earth blue, and the Earth magnetic field lines are equally blue. And Earth's is upside down dipole. You know that the magnetic field is the wrong way. It's actually, the North Pole is down here. But that's neither here nor there, and you have a lot of magnetic field lines. And let's pretend for the time being the solar wind magnetic field line is southward. We love to do it southward. It rarely is, but what the heck? Let's do the drawing that way. What's going to happen if on this reconnection site is that this part is going to talk to this part attached to that part. And so this is T0, T1, T2 as it's moving in. And now, oops, I was supposed to draw that in blue. And let's do this one. This is hereby called southward, yes. I did that wrong. This is this way. Okay, so this is a solar wind magnetic field line, we call that. This is an Earth or a closed magnetic field line. You see both ends close on the Earth. You can't get solar wind plasma onto that line. But now, the plasma from the solar wind can just run along the magnetic field line. As you know, plasma is frozen into its field line. It could travel along the field line any way it wants. So now you're going to mix. You're going to mix. Solar wind plasma is going to start bleeding in, and Earth plasma is going to start bleeding out into the solar wind along this field line. So that is why we would call this an open magnetosphere. This makes all the difference. If you have a closed magnetosphere, you're not going to interchange, well, you can through some instabilities like Kelvin-Helmholtz and waves. We'll talk about those later. But you can exchange on the flanks or some other way. But it's going to take some sort of turbulence or mixing to get these to exchange particles and energy. The key here is it's not the reconnection itself, which is fascinating physics. It's what reconnection enables. If these field lines reconnect, they break and they open up, all of a sudden the Earth is opened up to grabbing a huge amount of that solar wind energy and exchanging particles, right? Exchanging the plasma. Earth plasma is going to get out in the solar wind. We could lose plasma that way, but we'll regain some of the solar wind stuff. So we could see, for example, one of the tests. What is an early test you can make? So you're in early science, you have no spacecraft. How would you tell if solar wind plasma were getting in here? Should I ask you again? Pick on somebody else? Pick on somebody else. I'm going to ask you. Well, Aurora, yeah, but let's say I sent a balloon up. What would I look for? Alphas, maybe? Yeah, start looking for alphas, but you don't even need to send a balloon up. You could look for spectral lines that might come from an alpha, right? That wouldn't come from helium plus, or oxygen 6 or something like that, right? So those are the first tests you would make to see if you were an open or closed magnetosphere. Now we could fly a spacecraft up there, tell. Secret's out, we have an open magnetosphere. We do get reconnection. Sorry, I hate to spoil the secret. I was going to save it to the end. What the heck? So this basically is the process. So reconnection, this is why we talk about it a lot, is it's not just a process that is, it's a kinetic process that is happening in a very, very small region, but it has huge consequences. Do you see that? It's not just the reconnection itself and the energy release in the reconnection region, which theorists always yammer on about. It's what they enable. It enables a whole host of processes to go on that otherwise would not. Okay, so at this point, I'm going to say now, if we do reconnect, and Dungy thought of this many 60, 70 years ago, they were thinking of this. What happens to this reconnected field line? Yes. It has to be swept back, right? It's still, these ends are still in the solar wind. They're outside of the shock. Where's the shock? I haven't driven the shock. There's no black one. Anyway, shock, let's make it here. So here's the shock. The reconnection happens at the magnetopause. At time later, say T3, this field line, the solar wind part's just going to go straight back. It doesn't even know. It's outside of the shock. It has no idea the Earth is there, except for maybe some oxygen or something bleeding up the line. It doesn't care too much. It's going to go to that position. Same in the south. I'm only going to draw half of it now because it's going to take forever if I don't. And so on and so on until we get to all the way back here. Now I'm going to ask you what happens. So this is T4, T5, T6. So this is, you know, they're not. They should be even, but I didn't draw it that way. Take the picture up. Next picture. Okay, so you realize that if we keep doing this, we're going to take all the field lines from the front side of the Earth and move them to the back, won't we? I mean, field lines, here's the point. You can't just keep reconnecting and opening up field lines because the Earth only has so many field lines. If we opened them all up, they'd all be open. It's not going to happen. Okay, so they're going to reconnect again in the tail. This is an old joke because you have to have an equal amount of reconnection in the tail as you have in the subsolar region over a long period of time. Not on a short time. On a short time scale, you could build up magnetic field in the tail of the Earth. Okay, but ultimately, over a long period of time, this magnetic field has to reconnect and find its way back here somehow. We got to keep feeding magnetic field lines to this reconnection region. So Dungy realized that had to happen. This is the realization that he had, was that you had to have reconnection on both sides of the Earth. To begin with, to open the field lines, the process was reconnection in the subsolar magnetopause. But this can't, and the tail has no idea what's going on. It's just handed the aftermath of that. But the magnetic field just keeps piling up back here. Eventually, there's going to get so much pressure going that the magnetic field is going to reconnect here. Okay, I didn't draw these lines correctly. This is red, and so you'll get another reconnection point here in the tail. Okay, this field line now is it's highly bent. It's going to not like being bent. It's going to snap back towards Earth. How does it get up front again? It has to actually come around the side like this, out of the board and back in. Now, how do I do the Dungy dance? We have the actual world's best Dungy dancer here. That would be Fran.
Do you want me to do it now, or I'll do it next?
I was going to show him with a wire.
Okay.
Okay. So where's my wire? And then you could do the Dungy dance. So basically, this wire comes in, it snaps, right? Okay, it's going to drape, okay, reconnect, and now it's going to, after the reconnection of the tail, and I want to show you this, it's like this, right? Well, how is it going to get back up front? It's just going to go around the side like this. That's all. As a closed field line, it's going to go from the tail, which is your side, or let's make the tail Fran's side, just like this, up to the front again. Okay? So it's a three-dimensional process. A lot of students have huge trouble. I found this is interesting that a lot of people are great at 2D, but 3D ends up being a problem. But that's essentially what's going to happen. So that was the realization of Dungy, is that you had to have reconnection again in the tail. You want to do the Dungy dance? How's it work? You do.
Okay. So when you
I'm going to try too.
way, so you have a field line that's, say, vertical in the front, right? It reconnects here, opens up, gets dragged down the tail, right? Reconnects, comes back around the side.
Goes back up front.
So you do the double jumps.
You're being filmed, actually, so this is a good thing. I'm just a terrible dancer. So,
But it was invented here in this room for a previous year.
yeah, this is a really, so this is the Dungy dance. The fact is that the magnetic field is so strong at the Earth's surface that it's virtually incompressible. It is not, you can't create nor destroy that. Yes, sir? Yeah. But that's inside the magnetosphere. You see, you're inside the magnetosphere. There's no flow in it. Actually, the flow is sunward inside the magnetosphere. That is, it's very slow. I said 0, remember, but it's actually going back towards the nose. There is some co-rotation involved. Now, the Earth's co-rotation is very, very slow. In the next lecture, I was going to point that out. Fran's going to talk about real co-rotation, which is Jupiter. Jupiter rotates in 10 hours, which doesn't sound that much faster than Earth, but it's 10 times bigger. So it's going 2.5 circles for every Earth, and it's 10 times bigger. It's 25 times more rotation speed. So Jupiter has a rotation problem. The Earth, this whole Dungy cycle. Okay. Reconnection. Let's just do a quick. Yes, sir. I didn't get that. The footprint of the line has to move, yes. It's, as you get close to Earth, this is where I was getting to, it is a rigid dipole, closer in like this, right? So once this snaps back, it is now part of the Earth's dipole, and its footprint has to move. There has to be flow in the ionosphere as well, back in that direction. You'll find that this Dungy cycle dominates the ionospheric flow. There's going to be flow backwards, right on the top, on the poles. But in the lower latitudes, it's got to be forward. Because the magnetic field's incompressible to the Earth, it has to go in a circle. Magnetic field lines have to flow in a circle. If you have an incompressible fluid, the only way to get them to flow, sitting on a plane, the only way to get it to flow is to make it go in circles. Or a set of circles, or however you want to do it. So this basic cycle is the dominant process at Earth. We're going to find it's not the only process that can drive a magnetosphere. There are other processes, such as viscous drag on the sides, Kelvin-Helmholtz's instability, wind on waves, or water waves. There are a lot of other processes, rotation of the planet. Okay, but the Earth is pretty basic. The Earth doesn't rotate very fast. It just has a very simple Dungy cycle. Okay, so this is an important concept because we're going to talk about this quite a bit. Now, Dungy basically came up with this idea, but you've already been taught that magnetic field lines are frozen in. And back when he came up with this idea, the whole idea of magnetic reconnection required resistance. I'm sure you got that in the lecture, right? There is no resistance at the Earth's. Our collision rate is 0. The mean free path of an electron out where at our magnetopause is 1 astronomical unit. You would have to wait in there forever to find a collision out there. So how do you get any resistance going to get reconnection? That's what all the other scientists said to Dungy. Basically, you're full of it, is what they said to him. So the controversy on this process raged. So I want to stop. We've got this basic cycle, and I'm going to come back to it, because it's fascinating, and there are a lot of things that we could learn from this. Should we take a break now? I think we should, right? Take a break. Take a break. All right. 5-minute break. Yes. And practice the Dungy dance. This is great. I'm on slide 10 out of 90.
First question is, what determines
So we can do the math on this, and it's a simple math process. So this is around 10 RE, Mercury is about 60,000. 60 times 10 to the 3 kilometers, right? And this is 10,000. So let's just say that's 54 times 10 to the 540. Just say it's 300 times 10 to the 3 kilometers. 8 kilometers, right? Okay. So this. No. You want to make it? So let's make it 740, which is 10 or 15 arms. Okay. So we add this up. This is 800 times 10 to the 3 kilometers divided by 4 kilometers per second. What do we get? We get 2 times 10 to the 3 seconds. It's not quite an hour. Okay. So this whole cycle, this minus has to be about an hour. This part has to be 3 hours. Going to be over pressure because you won't get the reconnection unless you want the pressure scale. Yeah, so once you get the reconnection here, that releases so this starts to be higher pressure in the front, and that pressure pushes all the other fill-ups back. It ends up in the front, and depending on if it's a little red, it can go around the other side. Everybody says what happens to one example.
Why just break and then come back to the promotion?
All right. Well, actually, if you don't mind, I'm going to redo this for... he reminded me of another simple calculation I like to do in a class and ask you how long the Dungy cycle would take. Let's just get an order of magnitude estimate. Again, we're still in the back of the envelope stage. or the back of the iPhone or the napkin stage right now. I pointed out that this is, we know we calculated the standoff distance to be, say, 10 RE, right? It's 11 or 12. It really doesn't matter. We have a formula for that. These field lines, the red ones, travel at 400 kilometers per second. They're in the solar wind. They do not know the Earth even exists because they're on the other side of the shock. Remember, on the other side of the shock, the solar wind has no idea the Earth exists. So they're ballistic, and they've got a lot of friends to give them mass and momentum to keep going. So they're going to drag this field line back. And so I wrote down some distance. This is about 10 RE, which is around 60,000 kilometers. And then I said, hey, make this a large number, 100 RE, or whatever you want. It's less than that. It's probably more like 30 or 40 RE down. Okay, so I just did it 740 to make it an even number. So that's 740. Well, you'll see why. When you add these two, it gets to 800. And when you divide it by the solar wind speed, 800,000 kilometers, when you divide it by the solar wind speed, which is 400 kilometers per second, you see it takes 2,000 seconds for this field line to get stretched all the way back to where it may reconnect. Actually, that's long. It usually takes about 1,000 seconds. Okay, which is about 20 minutes. That's not very long, is it? And that's the solar wind speed. So it takes 20 minutes from the reconnection point back to where it has to reconnect again. And this thing has to take about 20 minutes, roughly, just to preserve magnetic field density at the surface of Earth to get back. So it's about 40 minutes. How far does the Earth rotate in 40 minutes? So who brought up the rotation? Do you see why I can ignore the rotation at this point? Because the whole cycle takes 40 minutes. And the Earth does not rotate very far in 40 minutes. It's only rotating like 10 degrees. So yes, it's a small problem, but for the 0th order, for the back of the envelope, we can ignore it. But not in reality, okay? So we're going to ignore it. But at Jupiter, by the time that it's 100 Jovian radii, it's going to take 100 times longer. It's going to take, 100 times 40 minutes, 1 hour. It's going to take 100 hours, 50 hours. Jupiter rotates in 10 hours. Jupiter's wrapped around 5 times by the time the Dungy cycles happen. So you could see in Jupiter, can you ignore rotation? Absolutely not. So in the Earth, you can. Jupiter, you can't. This is a beautiful comparative magnetosphere. All right, so let's move on. I want to talk about magnetic reconnection now. And magnetic reconnection is a kinetic process. I'm going to turn it sideways now. This is relevant to the direction to the tail, but you've all got to get used to the fact that in the subsolar region it's like this, in the tail it's like this. So what? It's the same physics process. The basic idea is that you have field annihilation. Magnetic field lines are inflowing from two different directions, or inflowing. They contact at one point, they change partners, and then they go out the side. This is, again, nature is so brilliant. That's why I love physics so much, is because nature thinks of things that we could possibly never think of. And when you find these things out, you go, wow, nature's smart. And, of course, they do a lot of simulations. They have many particles in their simulation. The problem with reconnection really stemmed 70 years ago from the fact that a lot of people felt that ideal MHD was usable. In other words, or resistive MHD was usable. That particles, as you know, gyrate around a magnetic field, and it's very hard to get a particle to fuse from one magnetic field line to another. And that is the heart of the reconnection process, is in the center region. I lost my pointer. In the center region of the reconnection. Meaning that as this field line comes in, the ions and electrons have to diffuse or jump some field lines in order to allow this process to move forward. And it sounds, by the way, I mean, reconnection is pretty trivial if you don't have plasma on the field line, right? Every time you shut your refrigerator door, you do reconnection. Okay, and I'm sure that happens 100 times a day. I mean, it's just, but if there's no plasma, magnetic field can annihilate or disappear or do anything. But if there is a plasma, since that plasma is frozen into that magnetic field, it's going to start creating currents and do everything it can to stop that magnetic field from annihilating. And that's the heart of the reconnection process, is how do you break, we call this the diffusion region because plasma has to diffuse across a magnetic field line. And so you must have a non-zero frozen-in condition, which is basically E plus V cross B equal to 0, is the frozen-in condition. So basically, when Dungy put forth his idea, it was controversies raged. Basically, the only place that reconnection was believed to happen was where there was a finite resistivity. Okay? You needed to have collisions. You needed to have resistivity between the ions and electrons. They had to bounce off of each other somehow, some way. But if, as I said earlier, I started this earlier, the mean free path of an electron or an ion at the Earth's magnetopause is an AU. There are no collisions, so to speak of. It's some small number, like 10 to the minus. That resistivity is so low, you've got to put a lot of numbers in your exponent. So this was the major controversy. Okay, yet Aurora kept going. We kept seeing aurora. We kept seeing solar flares. We kept seeing a lot of situations where reconnection was occurring at that time. So people really started paying attention and saying, what is doing this? Okay, what is causing this reconnection? And basically the idea was that if E cross E, curl of E has to be 0. If you have inflow here, you have to have an E into the board. And if you have to inflow here, you have E into the board. Outflow means E's into the board. That's all happy except for what's supporting the electric field here. That became the holy grail question. It's called the reconnection electric field. You've been told this. The holy grail of reconnection is what supports the reconnection electric field in this process. Okay, so we've been trying to understand that in the magnetopause because we now know the reconnection occurs in the magnetopause, yet we had at the time, even as much as 10 years ago or 5 years ago, we did not understand how it was happening. There were no collisions. There was a free fall electric field in the center of this reconnection region with no resistance, nothing stopping it. The other thing that was a major question is, where's all this energy going? If you calculate the energy flow, you're annihilating magnetic field, you must have a lot of heating going on. We could see these ion jets coming out of the reconnection region, but they're only carrying half the energy. The other energy must be going into heat. So how is that happening? We're looking for all these processes. So we decided not to, and many of you may have seen this. Now we're getting a little bit more complicated. This is called generalized Ohm's law. Okay, then if you do MHD without taking too many approximations, so now we're going to have to take a step back and say, hey, we can't just do MHD. We have to start putting in all the terms. We've thrown away a few terms. MHD is an approximation, so we're going to start backing out of these approximations slowly and see what approximations we made in MHD that's saying we can't have reconnection that we need to put back in to get reconnection. We're going back towards two fluid. We're going into kinetic theory. Do you see that? We're backing out of the big picture now. So the idea is we're going to take the full generalized Ohm's law, which says that you can violate this frozen-in condition with a number of things. You could have resistance. This is called the Hall term. It's the J cross B term, where you have a very, very sharp current that is normal to the magnetic field. Or you could have a divergence in the electron pressure tensor. We're not stopping at calling pressure of the electrons a a scalar anymore. We're doing the whole tensor. If you actually go back to kinetic theory and derive this fully, which I'm not going to do because I don't have enough time, you get a tensor, not, okay, usually it's diagonal, and all those numbers on the diagonal are the same, so we make it a scalar. Okay, 99% of the time, but not in reconnection it isn't. You're going to find that out. The final is, maybe we're just like saying, accelerating a lot of electrons. Maybe that's what's going on in this reconnection region. But in any way, when we start being a lot more rigorous about this, we look at all these terms. So this is where we stood. It took 50 years to get to this point, where we started looking at all the terms in MHD. Started realizing that MHD was not going to do this, so we had to back out of it. It doesn't mean MHD is useless. It's very useful. It's incredibly good. But we need to now go deeper. And this is, again, scientific process. When a set of equations or a set of formalism doesn't work, you have to say, hey, what did we make? What assumptions did we make to get this formalism? And start saying, well, are all those assumptions valid? And the answer is no, they aren't all valid. So we have to start backing out our assumptions. Now, this is no longer MHD because you can't have electron pressure. I mean, there's no such thing. It's just pressure in MHD. We cannot use these terms, so we call this, by the way, when we add this term back in, we call it Hall, MHD. When we add this in, we call it pressure, electron pressure term. So we're giving up on the resistive term in the magnetopause. That can work in some regions, chamber plasmas where there's a lot of collisions. But we have to give up and go to the Hall term or the electron pressure term in order to explain what is going on in this diffusion region at the magnetopause and in the Earth's magnetotail. Okay, so 10 to 10 years ago, a lot of simulations were pulled out and laboratory experiments were running and space plasma missions were flying. And this was a major, major question. How on earth is this reconnection, how on earth? How in the magnetopause and how in the tail are we getting reconnection? Okay. The first, this was, so there was, if you want to see a lot of papers, you just go back 10 to 10 years ago and start looking at reconnection papers, and there's probably thousands of them. People were trying to figure this one out, and the first thing that we found, which was roughly 20 years ago, was that the Hall term was critical for the ion behavior. In other words, when we ran, this is called the Reconnection Challenge, we ran simulations with MHD, and this is the reconnected flux, and this is time. And you can see MHD just can't do it very well, and that small amount of reconnection is due to grid error, okay, in the MHD. It's not really due to any physical process. Whereas when we started doing two fluid and full hybrid and full particle simulations, getting into the kinetic regime, the reconnection rates went much faster. In other words, we got the reconnection with full kinetic simulations, but we still don't understand why. Okay, we knew we had to add the Hall term up. So Hall MHD started working to get the fast reconnection rate. But I want to point out a problem with Hall MHD is J cross B is the Hall term over En. If you take J plus P dot J, it's 0, so it can't dissipate energy. So it didn't help in the energy problem. It just helped us. What the Hall term does is say that the ions can, because there's so much pressure change there, they can actually jump field lines via that term. So that's the, if I go back to that generalized Ohm's law. Oh, I'm going the wrong direction. Generalized Ohm's law here, the Hall term basically is breaking the frozen-in condition for the ions. But it is not breaking them for the electrons, is what we found. So how do we get electrons? You know, they have really tiny gyro radius. You guys know all that? So they're really stuck to their field lines. Ions, they're big lumbering things that go way around, so they can get off their field line in a lot of different ways that electrons can't. So it was a lot easier to figure out how the ions are jumping the field lines. But how are the electrons are doing it? So we started looking at this electron pressure and the electron inertial term, saying those things must be active in order for reconnection to happen. So where was I? I was at this GEM challenge. And we invented a new diffusion region. So we realized the ions and electrons are not behaving well, and the same. So a much larger region, the ions could jump off their field lines and diffuse out, but the electrons must be jumping the field lines in a much smaller region. So all we did with all this work is invented a new diffusion region. The ion diffusion region and the electron diffusion region. All the literature prior to 20 years ago just had the diffusion region. Then all of a sudden you have two of them. So this is progress. This is progress. We didn't understand a diffusion region, so we broke it into two and said, oh, okay, we'll figure it out. All right, that's progress. So it was this electron diffusion region then were giving people nuts, driving them nuts. We had a lot of kinetic simulations going. We started seeing in the kinetic simulations some progress, but there was a lot of controversy of exactly what was doing the breaking the simulation. So breaking this frozen-in condition in the reconnection region. I'm an MMSer, as you all heard. So this is where we stood about 10 years ago, and we were about to launch 4 satellites that had the ability to actually determine what was going on in an electron diffusion region, say at the Magnetopause. I only have 10 minutes left. Is that real? Okay. Well, I'll give you the rest of this tomorrow, eventually. We'll finish this part up, though. The idea on the magnetospheric multi-scale mission was to put 4 satellites in a tetrahedral configuration. That way we could take derivatives. We could take full derivatives in 3 dimensions. You need 4 satellites as a minimum. And so we have separations in X, Y, and Z. And we could take derivatives and we could watch this reconnection process occur on the smallest of scales, all the way down to the electron diffusion region size. Okay, so the other thing that we did was we used this back of the envelope, or previous missions too, physics to understand how we're going to get into a reconnection region. We knew exactly where it was happening at this point. Earlier missions had no idea where the reconnection was happening. We knew because we took advantage of those. So this is basically a second generation mission where we're going on prior knowledge. This is not a discovery mission as much as it is, hey, let's go figure out how it works. And we were going to go first to 10RE and just hang out there. If you put your apogee of a spacecraft from orbital dynamics, if you put a highly eccentric orbit, it just hangs at its apogee for a long time. So our idea was basically go out there, hang out there, and we woof around occasionally after orbit. But we're going to try to get this. The first thing we saw was that the reconnection region was not exactly symmetric there. It was highly asymmetric. It was pushed back badly by the ram pressure and the pressure in the sheath. Remember that sheath we just thought it had particle pressure, remember? It has a lot of ram pressure left in it. And that was actually bending. Oh, I've switched it. Sorry, but half of our field puts the sun on the, what would be your left side. The other half puts it on the right side, okay? And I've gotten so screwed up it doesn't matter to me. But the sun is now on your right side, because that's the way this person wrote this article. Okay, so the solar wind's coming this way, all through my leg. I'm a left side. I'm a leftist. This was a right-wing person. So this right-wing person comes in, it's ramming. The solar wind's ramming, and what's going on with the magnetopause is it's getting pushed into Earth and bent. So this is the magnetopause, what it looks like. It's usually this thick, but it's just getting rammed and thinned out, almost squished by the solar wind. That's where the reconnection site is. Okay? And so in real data, when you see a reconnection site, in the subsolar region, what you expect to happen is on one side, which is the magnetosphere side, which is here, Z is in which direction? It's northward, right? B, the magnetic field, is in the Z direction. Z is the which direction. B is in the Z direction, which is northward. Okay? And on the other side, on the solar wind side, it's got to be somewhat southward, meaning it's got to be negative. So we call northward positive. And so look at the red line here. The red line is this red line here. We're kind of in the magnetosphere, but we're sort of wiggling around and things are going a little unstable. And then all of a sudden, boosh, B goes negative. The red line is the Z direction of B. So we have now gone into a solar wind region. We have crossed that magnetopause. So it's right here where we crossed the first time, where we take a really close look at the data. Did we or did we not hit a reconnection site? And bingo, we did. Okay? We hit the reconnection site. Now we've gone from a minute or so to 20 seconds across here. That's all we get. In fact, we were only in the reconnection region for 2 seconds. We actually hit it, but we were only in there for 2 seconds. But that's okay for us because we measure things at 16,000 samples a second. I mean, we got so many samples in there, it's unbelievable. Okay, we're just measuring like crazy, okay? So what we ended up seeing was we got the dissipation. Look at J dot E. Boom. There's the magnetic field annihilation. If you're going to annihilate, you guys all know Poynting's law? Poynting's theorem? If you're going to annihilate a magnetic field, you've got to have J dot E. That takes electromagnetic energy and turns it into particle energy. I could write it down. I don't know how to write it down. I only got 3 minutes left, but I could write it down. So, what? Okay. And I'm just going to put this... and I got a phone call, too. Sorry, I can't take this phone call. Okay. So, minus. Oh, no. Usually this is written with the minus sign here. So if you're going to have annihilation of magnetic field lines, you have to have either Poynting flux going out of the region or you have to have dissipation in the particles. We already determined you can't have Poynting flux going out very easily, so you need a J dot E.
I can't read that squiggle.
Divergence dot S, which is Poynting flux, equals mu naught E cross B, friend. Okay, all right. We kid each other. The basic idea here is that in order to have that, and this was really unexpected to have that magnitude, but that is how small the electron diffusion region is. That's where all the action's happening. That's where the field lines were being broken. We found it. We hit it. And then we've hit it 30 times now in the subsolar region. And so we had, we're in there. Let's look at the electrons. We're snapping electrons like mad. We're basically, this person's persistent. We're basically trying to get distribution functions to find out exactly what was happening. And at the exact moment we had one spacecraft and the other straddling the reconnection region, there's lots of ways we could tell that we were doing that. We ended up seeing electron distributions where the electrons were no longer going around in circles. Okay. Okay, so we were looking at this is kind of a cartoon of where we are. Okay? And what this is this is the parallel direction, and this is the perp direction. Other way around. This is perp, this is parallel. This person is not only right-winged, but they're rotated. And if the electrons were, I'm sorry, this is perp-perp. This is perp-perp. If the electrons were going around circles, this should be completely round, right? It's telling you how many electrons are going this way and how many electrons are going that way. So the position in that is the direction of the electron flow, electron velocity. So you have more electrons going. See, if electrons are gyrating around a magnetic field, then they're just going around in circles, right? So almost every time you measure electrons, you get a round distribution. The distribution was no longer round. Okay, so that told us something. We were breaking the frozen-in condition there. Okay, so we had to figure out what was going on in that. And it turned out that there was an off-diagonal term in the electron pressure gradient, tensor. I know you're all dizzy now, right? You must be all totally dizzy. Good, because this is a really big finding. It's in science, and the idea is that it turns out it was a really simple idea that we should have thought of a long time ago. So let's just say the X line of the reconnection is this way. We're trying to understand how you could support an electric field in there. What happens, the electrons wander in, and they start getting accelerated in this free fall region where there's no magnetic field and just an electric field. And they start accelerating along that. So we said, hey, what's stopping that? Well, they just wander out. So we're taking momentum in this direction and transferring that momentum, moving that momentum in a lateral direction. That's the off-diagonal term of the electron pressure gradient. That's what it means. Is you're taking momentum in one direction and moving it in the other direction, 90 degrees to it. If you're dizzy, it's okay. I know you guys are seeing this for the first time, but it's okay to be dizzy now. Okay? Point is, and I'm going to come back for air now, become simple again, is that you can see how this little process, highly kinetic process of breaking an electron gyro, causing an off-diagonal term in the electron pressure, is massively consequenting the whole Earth's magnetosphere. It opens it up. That teeny little process happening in a teeny little region is critical. If that didn't happen, there would be no open magnetosphere. So this is a real lesson, I think. The beauty of this is we've gone from a large scale, using MHD and showing open magnetosphere and everything, down to the tiniest scale and showing how these little tiny things, the teeniest thing, is causing this massive, it's like the ant that causes the avalanche. Okay? So, no, seriously, that's what it is. It's an ant that's causing an avalanche. And a teeny little bug gets on top of the hill, and all of a sudden it avalanches. Well, that's it. So this is the process that we were talking about in this. All right, so let's go back to this Dungy cycle for a little bit, and I'm done. Oh, you're giving me 5 more minutes? I got 5 minutes overtime. Okay. That's all right. Dungy got an E in it? Holy mackerel. All right. All right, Dungy has an E in it. So we're going to go back to Dungy and talk about the tail. So what I want to, and I'll start this tomorrow morning, I'm going to go to the tail after this and finish up the story, okay, with the tail. And we're going to go a little bit easier, so we're backing out. I just gave you a taste of kinetic physics and research, how you start wide, start at the back of the envelope, and then you build a big mission. I don't think it was built from the envelope. But you do some more calculations, do some simulations, then you build a big experiment, then you get your results, and then you really understand what's going on. And we're going to try to do the same for the tail. The tail makes up its own mind, though. The tail's like that little bad boy who just won't do what it's told. Okay? Once reconnection is pretty steady state here. The Earth's magnetopause, the reconnection is driven by solar wind coming in, the shock solar wind. Remember, it's changed. It's shocked. It's changed to higher density, higher temperature, and everything. It happens. The tail has no idea it's happened, but it's told it must reconnect this and let it go forward. But it doesn't say, no. It's not going to do it. It basically resists it and resists it and resists it and says, no, 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 no. And magnetic field basically starts building up here and building up and building up to the reconnection, to the pressure of all these magnetic field lines piling on, all of a sudden, bang, explodes. When the tail reconnects, it doesn't do it slowly and steadily like the magnetopause. It does it explosively. So it's a buildup, and then boom. Okay, it will reconnect a ton of a magnetic field, and then it will go back to saying no, 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 until it gets so much pressure, it bursts again. Okay, so those periods of bursting are called substorms. Magnetic substorms and magnetic storms. And we'll talk about all those on Friday. So I should stop and ask any questions that you'd like to have before Fran ruins everything. Sorry, we are good friends. Takes and teaches you all about Jupiter and makes you think a rotation does everything. Okay? I'm a Dungy cycle person. She's a rotation person. We all have our ways, but she works on Jupiter, I work on Earth. So any questions? Yes? Well, the reconnection rate's going to slow way down. The question was, what happens when the IMF is northward? Okay, the IMF is never really southward or never really northward. I didn't mention this in reconnection, but you don't have to be exactly anti-parallel. You could just have to have an anti-parallel component. You see what I'm saying? So unless it's really due north, and by the way, the Earth's magnetic field is twisted enough that there's somewhere it will reconnect somewhere. But it slows way down when the reconnection at the front end slows down when it's northward, speeds up when it's southward, is the basic answer to that question. Yes? Okay. B squared energy goes into your arm or into the door of the fridge. If you're pulling two magnets apart, you're creating magnetic field, right? And when they come together, they snap. That energy goes into the crash of the magnets, into the door shutting. Or sound or whatnot. Yeah, that's a basic physics. That's a cool thing. I mean, you pull two magnetic fields apart, you're putting energy into the magnetic field. When they come back together, you could pulling. If you push two together, by the way, you're creating magnetic fields. If you flip them over, you know. That's a good, question for, grad students. Yes. In the data, there's not resistivity per se, as I'm trying to say. That resistivity is caused by the fact that the electrons can only dwell in that free fall region for so long. We see that in the data, and simulations saw that prior to us, but nobody was convinced that's what was going on because it was a 2D simulation. But in fact, reconnection obeys a lot of the stuff we've seen in 2D simulation. 3D simulations are much more turbulent, and we see, if you saw that reconnection region, it was turbulent. It was wiggling a lot. So there's a lot of, it's not as well behaved as it should be, or as we thought it would be. Yes, sir. Mm-hmm. The spacecraft are only moving about half a kilometer a second out there. And that's not the problem. The problem is how fast that magnetopause boundary is wiggling like this, it sort of wiggles. But it was moving around 10 kilometers a second. So we were in the ion diffusion region, which is about 20 kilometers. The electron diffusion region was only about 0.2 of a second. Actually, that spike, which was only around 2 or 3 kilometers. We knew that going in. We knew that going in. We did a lot of back-of-the-envelope calculations before we built these spacecraft. All right. Well, one more?
So there is a reconnection, it's polar reconnection. So
Right. Oh, no. If you thought what I said about reconnection was twisting your head, that's real brain damage. The answer is I could talk to you offline on that. That's just the brain damage explanation. Particularly when it twists east and west. You know, you twist the poles and you also get this direction too, you know what I mean? It gets really messy in a hurry. There. I didn't realize that. You should. Yes, excellent. That's very good. Now that's a good part. So you could see what happens. I always like to teach the easiest thing because, yeah, I mean, again, this is science. You start with the easy part and then you start adding all the, the low-hanging fruit, and then you start adding the complications into it. And it really does cause severe brain damage to not have a southward IMF, let me tell you. I've already got bad brain damage, so yeah. Anyway.
Why don't we do 15 minutes?
She's going to do the Jupiter rotation dance.